access to new biotechnologies. And this includes everything from, you know, modern DNA science, personal genomics, things like that, synthetic biology, to this trend now to use biomaterials instead of synthetic materials. Things like mushroom mycelia as building material, or bacterial cellulose as clothing, perhaps sustainable design. And we give courses for the general public. We have lab memberships, which for a pretty low price point, $100 a month, you could come in and use the lab for a project of your own. The only thing we care about is it's safe. But we don't make any judgments as to whether we think it's a crazy project or a good project, or if it's going to succeed or fail or make money or save mankind. Just as long as it's safe, we're pretty much okay with it. We run student events. We had one of our former iGEM team members is here, the International Genetically Engineered Machine Competition. So we have events for students, and we also curate various art science events, both internal and external. This is part of our talk series, and we've had everything from artists that see history through the eyes of animals to scientists working with nanotechnology at the smallest scale possible. So our talks really run the spectrum. We are a not-for-profit, so there is a donation box here next to the food in case you're interested, and we appreciate it. And we are very, very happy today to welcome this really extraordinary team of people that won this prestigious award from NASA, and I'm going to let Ricardo, our Director of Outreach Events, introduce them.
Thank you. Welcome to GenSpace, and welcome to this presentation event tonight. This is most likely, well, at least for some time, the last event that I'm involved with, because I'm going back to Spain, going back to Barcelona on Thursday. I've been a volunteer in GenSpace for nearly 2 years, year and a half.
Oh, more than that.
More than that. And it's been amazing working here, and my idea is to bring back all these good vibes and knowledge and this sort of biomaker space model back to Spain, back to Barcelona, Madrid, and maybe other European cities. And I would like to, of course, stay and keep collaborating with GenSpace and probably organize events on both sides of the Atlantic Ocean if we can.
I want to go to Barcelona.
And of course, everybody's invited to come to Barcelona. Well, the story starts like many other stories. Here in New York City, you come across amazingly talented people all the time with amazing projects. And my friend Sumiko, who is also a very talented singer, she's here with us, and she invited me to a dinner, and I met a group of very talented architects during that dinner, and I found out that they did these amazing projects about building a house on Mars, and they presented this project to NASA in this international contest, and well, they presented something amazingly innovative and different and radical and beautiful, and they won this contest. So immediately I was asking them, would you like to come over to GenSpace and present this, see what we can do out of an evening around this topic, and hopefully maybe this has future activities related to, you know, space architecture or terraformation, astrobiology, and so on here in GenSpace in the future. I will let the speakers present themselves and talk about this amazing project. I think the way it has happened, the way it has been developed from my conversations with Masa and colleagues, it's amazing the way that they found solutions, and the whole process behind it is incredible. And I would like to make this sort of a bit of a dynamic, more dynamic and engaging presentation. So, you know, it would be, if you guys have questions during their talk, there's going to be questions at the end of the presentation. So there's going to be time for that. But if there is a specific questions directed, you know, very much to do what is being said at the moment, feel free to raise your hand and to ask those questions. And I hope everybody enjoys this for sure. Welcome, guys, and thank you for being here.
Thank you. Thank you for inviting us here to GenSpace for this presentation. We're a group of actually two groups. One group is called SEARCH, which is Space Exploration Architecture, composed of 5 individuals. Jeffrey Montes is here, Kelsey Lents, Michael Morris is here also, and then Melody Yashar and Christina Ciardullo are not here, but they're here in spirit. And then the other side of the group is Cloud's Architecture Office, which includes myself, which is Ostap, Masa, and Yuko. And there will be like a credit screen, so I can show you more formally the kind of team structure. I just want to start, I guess, in the spirit of kind of the open dialogue, asking you guys a question. Has anybody seen this project before? If you could raise your hand. Good. Can everybody see the image, or should we kill the lights? Kill the lights? Is that possible?
Yes.
Great. Okay. So I'm going to start with an introduction, and basically we've broken the talk into chapters, and each of us will cover a chapter. So I'll basically introduce the framework of the competition and some background information about Mars, which is the context for this project. NASA teamed up with America Makes, which is a 3D printing trade group. And to help hold a design competition, which is run from May to September of this year. And they stipulated these requirements on the left-hand side and the judging criteria on the right-hand side. So essentially, the requirements were for a habitat to house a crew of 4 astronauts for a duration of 1 year. They gave a size, like a 1,000 square foot footprint, which is basically driven by the environmental control system. So the oxygen and CO2 scrubbers can only manage a certain volume. And they gave us a kind of general program, including hygiene areas, bedrooms, cooking areas, etc. And they stipulated that we should use 3D printing involving indigenous materials. So the motivation behind the competition is that it's very expensive to bring material into space, right? So if you can minimize your payload and use what's there as much as possible, you're like miles ahead. So using 3D print technology, which is sort of a recent phenomenon, they asked the entrants to come up with a 3D printed habitat design. So this is the team. As I mentioned, it's composed of 2 sort of distinct entities, Search and Cloud's Architecture Office, as well as a whole cast of research consultants, including planetary geologists, structural engineers, which are here in the city, Leslie Roberts and Associates, radiation specialists, a whole cast of characters, and they all kind of had their input at various points throughout the development of the project. So the context, the site itself. Mars is in some ways similar to Earth, and in some ways it's very different than Earth. Its atmosphere is much thinner than Earth's. It's about 1/100th of Earth's atmosphere in terms of the density of it. And the composition is quite different. It's primarily carbon dioxide, where ours has very trace amounts of carbon dioxide. The pressure is also quite different. It's like a near vacuum kind of environment. In terms of the sun, Mars is about 1.5 times as far away from the sun as Earth. So the amount of solar flux, like solar energy that's reaching the surface, is 40% of the Earth's. So using solar energy is a little bit more challenging. You need more surface area to get the amount of solar power. Their day length is very, very similar to ours. It's about 40 minutes longer than our day, and the year is about twice as long. So because the orbit is further away, it takes longer for the planet to circle the sun. The size and gravity, it's about half the size of Earth, and the gravity is about 1/3 of Earth. So you can essentially jump 3 times as high in Mars as you could here, and structural members can span longer, and you can use lighter weight framing material, let's say. Additionally, the axial tilt, the obliquity of the planet, is very similar to Earth, which means that Mars also has the seasons of Earth. Except their seasons are actually twice as long as ours, so because of the longer year. The distance is significant, so getting there is a challenge. Actually, you have to kind of time your departure and return in terms of the alignment of the planets, the orbits of the planets. So a typical mission might be 2.5 years, which involves about 6 months to get there, a year on the surface, and then 6 months to get back. Mars itself has some of the most extreme topography in the solar system. It has the highest, biggest mountain and the deepest canyon. These little travel brochures are made by SpaceX. They're planning to put 1 million people on Mars within 20 years. This is like a roughness map of the surface, so like the terrain roughness. And because the atmosphere is so thin, the surface is exposed to radiation. So you get bombarded by solar radiation and cosmic galactic radiation. So basically, I think they're saying that the first meter of the planet is basically sterile. And as well as comets. So the surface is pockmarked with craters. The surface is also covered by a layer of dust called regolith, which often get kicked up into large dust storms, which at times can cover half of the planets or even the full planet, full face of the planet, which is another challenge for solar power. The temperature range on Mars, these are the extremes, so you'll get negative 133 Celsius on like the polar winter, so on the extreme poles in the wintertime, that's a low temperature, up to about 80 degrees Fahrenheit or 27 C, which is in the summertime at the equator, so there's quite a range. And these are temperature maps of the surface, and at the bottom you can see, on a December day what the range would be. It goes from negative 125 to 20 C, like the red is about like 60 degrees or so. And then these are also like September days, like a daytime and nighttime, so you can see the variation in the same day. Water. So this competition took place before the announcement of liquid water on Mars, but we already knew that Mars had significant amounts of frozen ice water, to the extent that if you melted all of it, it would cover the surface of Mars to a depth of 10 meters or about 30 feet. So this is a visualization of ancient Mars. Like if all that water was actually liquid, it's hypothesized that there are large seas, large oceans on the surface. And that chart on the right-hand corner shows the progression from 4 billion years ago, 3 billion to 1, and now. So basically the water, because the atmosphere disappeared, the water was sort of trapped in the ice of the poles. In 2008, we sent Phoenix, which was a lander, and Phoenix, when it landed, the thrusters blew away some of the regolith and exposed ice. And so then they took a shovel from Phoenix and kind of started digging, and this is what they saw. They saw water ice just below the surface. And the right-hand side, you can see the rate of sublimation over 4 days. Like the sol is actually 1 day, so you can see that the ice has disappeared over 4 days. Some more data maps. The left-hand corner is the hydrogen abundance, which is assumed to be like a water equivalent. Red is the high concentration, so most of the water is at the top and bottom of the planet. This is a perchlorate distribution map, which is one kind of side note is that some people believe that the regolith is toxic. Perchlorate, when it's inhaled by a biological life form, causes a lot of problems. And then the silicon distribution, silicon can be used to make glass. And then the dust index, so this is kind of the dustiness of the planet. Using these kind of maps and overlaying the different criteria, the different data of the various characteristics, we were able to kind of hone in on a site. This happened later on in the process, once we kind of had an idea of what we were doing. But we chose a site that's in northern latitudes, close to the pole, a little bit below the Phoenix landing site. So that image of the kind of exposed ice, that's a little bit north of our site. So the site is called Montes, and those are the latitude and longitude of it. This is a kind of an idealized site plan showing the habitat in the center and distribution of the power array, the communication center, and the cache for food. And then these are landing ellipses, which I don't know if you know, but to actually land a payload on Mars, there's very little accuracy. The window or the footprint of the landing is about 4 kilometers by 12 kilometers at the moment. Hopefully in 20 years' time they'll be able to kind of focus that footprint so we can get more precise with the landing. But the other key component of this is access to ice. So the gray areas are assumed to be subsurface ice deposits, which will need to be nearby. Another criteria that we looked at is planetary protection, which might be interesting to some of you, the biologists. In 1967, there was a outer space protocol that was signed by 104 nations agreeing to essentially protect celestial bodies, meaning that we can't contaminate them with our own biological material. So the top left is an image of the Viking mission from the 1970s, and they essentially baked the spacecraft at 120 degrees Celsius for 30 hours to basically kill all the spores and bacteria on the spacecraft. And then, of course, with any mission, you have all kinds of detritus. So that's the surface of Mars. Those are like shields and fairings that drop off during sort of the delivery of payloads. And then this is on the moon, where like an old probe is being visited by a new kind of visit from the Apollo team. So you can see the Apollo spacecraft and how close it landed to the old probe, and they sort of came up and took pictures of it. And what we know is that probes have bacteria on their surface, and so they limit the spore count to 300,000 spores per craft, or about 300 spores per square meter, in terms of what you're allowed to bring to a celestial body, another planet. And when it comes to a manned mission, it's a whole different story, right? Because people are just bacteria bags, basically. And so this is a spacesuit with all of its various moving parts and joints. There's something like 30 different joints, and they all sort of leak inevitably, and spacesuits also vent because when they build up pressure, they need to release various gases. So this image in the middle is actually from Apollo 12, and it's one of the few images where you can actually see the kind of mist and vapor of the venting of the spacesuit into the kind of lunar atmosphere. So suits leak and also habitats leak, right? So they also need to balance the gases and the pressures inside, so they're going to have to be able to vent and leak their environment to the outside. Some of the precedents that we looked at from the 1960s and primarily the 80s, these three are from the mid-80s when the Bush Senior, no, it wasn't Bush Senior, but there's a lot of interest in going to Mars. And you can see that there's kind of a common element with them that they're usually sort of spherical, underground, partially, and also they have inflatable components. And these are kind of updated, more modern versions of the prototypes that they're looking at now. Again, it's like an inflatable kind of pressure volume without windows. And this one is actually intended for Mars, where they have a rover that docks right up to the habitat, so you don't actually have to go outside to get into the rover. This is the European version. Again, no windows. And Mars One, which is a private venture. And essentially it consists of the transit vehicles, which are the capsules. They would just actually be landed and sort of somehow arranged into this neat line and hooked up. So you're going to end up living in your transit vehicle, although they do have plans for extending them. And this is maybe the most current and sort of updated version of an outer planet habitat. This one is on the moon, and it's by Norman Foster, which is a European architect. And it consists of a module, a landing module that then is inflated. Part of it is inflated, and around that sort of inflated dome, they essentially just kind of cover it in regolith, like 3D print regolith around it to create this protective shell. And the interior again is windowless and dark. Basically, what we found is that most of the habitats are cave-like, without sort of a connection to the landscape and without access to the natural light. So out of this kind of research, we developed basic design criteria. The meta requirements are what came from the competition, using indigenous materials for a crew of 4, autonomously constructed, etc. And then we also added our own sort of architectural criteria. Because this is sort of, it could potentially be the first piece of architecture on the Mars, we felt that it needed to be iconic and have, celebrate the human presence on Mars, to have some kind of cultural value, right? Some image that can people can identify with. Also, the architecture should provide visualized stimuli using natural light or changing color. It should also allow for changing imagery, so if there's a window to the landscape and the landscape's changing, that satisfies the criteria. It ensures crew safety, and also we wanted to protect Mars from contamination of humans, right, forward contamination. As well as establishing vertical orientation in the landscape so that it has some presence in the Martian landscape, something that can be visible from a distance. As well as having a variety of spatial qualities, so from common areas where the crew would get together and eat to their own private quarters, and then these sort of also in between spaces, like a kind of intermediate zone that is not programmed, that they can actually go and sort of unwind. And throughout this kind of criteria, there's a psychological factor. When people go to Antarctica or like into submarines or do kind of these long, deep missions, it's been found that actually the most kind of difficult criteria is the mental criteria, the kind of psychological factor. And so, when you're spending 6 months in a capsule and you arrive on Mars, we wanted the crew to be able to sort of unwind, to be able to stretch their legs, to kind of walk out and kind of stretch out a little bit. And that kind of sort of more normative connection to the landscape, like we have here, like kind of being able to walk out to some degree and look out to some degree, is what we felt was really the value of the project that kind of distinguished it from the kind of precedents that we were looking at. Yeah.
Okay, so next chapter is kind of architectural design process. And when we started discussing with Ricky about this presentation, first thing he kind of mentioned was he's very interested in the kind of process or the thinking behind it. So we thought that was great. And nowadays everything you think is on the web, but actually like those kind of process behind is typically not on the web. So something special that we can present to you. And also we thought we're going to bring some process studies and sketches that led to the final solution. So anyway, Jacob, then welcome to the backstage of the architectural design. So when we started the kind of initial sketches, just 8 of us just brainstorming, gathering, and showing ideas, discussing. So this was some of the sketches that came out in the initial stage. And we have to confess that we started with the regolith structure, like the president, the ideas or stuff that presented from the past. So that was our departure point. And so these sketches, for instance, it is different from what we ended up as the final solution, but there's a lot of ideas that led to the solution. So for instance, this is like Gustav was mentioning, one challenge is to how you shield from the radiation with very strong, and you need a very hefty shield if you use regolith. And we're also interested in how we kind of integrate into the landscape or the sun orientation, prevailing wind direction, and so forth. So that was one idea to fit into the context of the landscape. And we're also very interested in internal aspects, human kind of aspects. So this was idea of having a hydroponic garden in the middle that would obviously physically, create oxygen and so forth in food, as well as raising plants and seeing green is very good for human psychology. And something like this, very minimal, simple, and very iconic silhouette or form that stands out in marginal landscape, that there's no man-made structure. So, and this is more the vertical idea of the vertical volume in the landscape. And this is kind of using the regolith as a foundation, but the habitation area is actually inflatable element that kind of weave into the regolith structure. And the one big, among these ideas, one big idea we really wanted to achieve was something like this, the big view to the landscape, this amazing marginal landscape. And both physically to, gain natural light for not only for energy purpose, but also psychological well-being of the astronauts, because the cycle of the Mars is actually very close to Earth, like 40 minutes difference. So using the natural light for human, the cycle would be very helpful for the health of the astronaut. And the other idea was this kind of layered space idea. You can see the habitation here, and then there'll be like a buffer space that in between the outside, very harsh environment, and human space. So you're not right next to the harsh, the outside space, but there's a buffer space that helps both directions, meaning that, like what I mentioned, there's a concern we don't want to pollute the Mars. So we can control the elements that bend out from the habitation area into this intermediate space before it goes up. And then also, psychologically you're in this, but there's a space in between. That's either kind of not inside nor exactly outside. It's in between space that would kind of buffer you from buffer you psychologically from the outside space. And the biggest challenge was the radiation, because it's how do you kind of shield the radiation at the same time, creating this big opening, natural light and view over. So through our research, we found out that actually water is one of the most effective shielding material for radiation. This was done test done in International Space Station. What they used was a wet tissue, like a napkin, wet napkin. They bundled it up like 6 centimeters and then did a measurement for the radiation. This is the results. The red is actually with the tissue covered, so it dramatically reduces the amount of radiation compared to without. So we thought ice has amazing potential because it is so much ice on Mars. It's an indigenous material we can use, and then it's a source of life. Wherever we go, we have to have water anyway to survive. So it's going to be there no matter what. And then it's a very effective radiation shield, and also it transmits natural light and potentially a view out as well. And the natural light would also help for the plants inside for the garden. And it also made sense to think of ice because the average temperature of Mars is below 43 Celsius below zero. And it is very energy efficient in terms of creating ice. So you don't have to use high electricity energy to create for instance, sintering the regolith or creating metal from the legless and so forth. And lastly, it is a very natural material with kind of an aesthetic to it. It's a very beautiful object as well. But another challenge was, okay, so we're going to use ice, but problem is ice on Mars is something, it's like a dry ice on Earth. Because of the low temperature and atmosphere, it sublimates from ice to vapor. So there's, once you expose the ice, it basically evaporates. So how do you create the shelter or shell using ice? So through our research, we found this study done by a Romanian engineer called Stefan Carr. And his concept was very interesting to us because he was studying about creating a shell in outer space, basically using sort of transmission of a water chemical stage and using the vapor of water as a medium for basically three-dimensional 3D printing. And for instance, there's if you pressurize a certain volume using transparent films such as ETFE, which is high strength, UV resistant, transparent, inflatable volume, then once you inject water vapor with a sublimation effect, it will, with a fan, the help of fan, it will gather to the inside surface of the volume, and once contact with the outside temperature is so low, it will start freezing. And so it's not a conventional 3D printing like layered stacking, but it's actually like a real 3D in a sense, the additive manufacturing. So we thought that was a great concept and tried a bunch of studies. And this is just part of what we do. We have tons more of these, but I can't show everything. But just wanted to show a little bit how we work. We just come up with a bunch of ideas as much as possible. And the thing is, funny thing is, a lot of times, a great idea comes from really dumbest beginning point. And because what's most exciting to us is when we come up to a solution or design that's very unpredictable. If you can predict the finished product from the beginning design, it's boring, right? So we try to come up with as much as ideas and find a very right solution that's not unpredictable. So this was first submission, but the competition was in 3 stages. So this was the first stage. We had sort of a low profile, asymmetrical volume with just a landing element, lander, that comes first with the stuff inside these materials, the membrane and the printing machine and so on. And then we have basically 2 layers. The first layer will be the ice, the outside, the shielding. And then another inside layer for the habitation area that is insulated, so it's warmer. And in between space that we mentioned before, and the hydroponic garden in the middle. So it had a redundancy effect that you're protected by kind of a 3 layers under the inner shell and the outer shell. So after submitting, we kind of discussed with our engineers and scientists to develop our project. And first thing they told us was the form, asymmetrical form, is not very efficient. That's what they, that's how they think, because the engineers very concerned about the efficiency and so that was one thing. And but that was our scheme. This was your sketch. But we wanted to, like also mentioned, we wanted to achieve kind of iconic, unique identifier or kind of asymmetrical kind of volume with a spirit, basically. So we went on to study more with somewhere in between, not freeform like the first one, but not completely symmetrical like the dome, but somewhere in between, using a cone, the composite of cone. So it's essentially still a platonic geometry, very pure form. But at the same time, we compose so there will be a direction to the space, and these crease lines that emphasize the asymmetry direction. So out of these, we kind of picked, or more, we picked simplest one essentially, the kind of shard-like form that jets out from the ground. So this was for the second submission, second stage. So here you can see what we did was we rotated the lander so it's vertical, which we found out through our research that the lander makes sense, the inside actually vertical configuration. So which gave us the opportunity to have this the height as well from more of a landmark. And then the lander is completely contained in this inside layer, which is circular in plan. It's rotated simple geometry. And then another outside shell, which is a composite of the cone. And further, the second submission was kind of unresolved was the connection to the axis. So we further studied how can we efficiently solve those functional aspects. So we pushed the inside volume towards the north side, which is here, but where the rover attaches. And so what happened was, in plan, the two would come together at the north side where the lander connection. The intersection, at that point, the two shells actually come together, forming a single shell, which makes us opportunity for windows and thinner area of the ice. It's not a double. So we have two axis airlocks, one for the rover to directly connect, so people can go in and out without going outside, and then for the person, the emergency exit, smaller one, the south side. And so having these elements plugged into this pure form is always kind of a challenge, because we want to keep the purity of the form at the same time fulfill the function. So what we did for these elements, we kept the form, the original pure form as is, and just shaved the edges. So the shading creates a flat area of these triangular slivers, and there we have we created these airlocks. We inserted these airlocks in the flat face, so we don't compromise the overall purity of the geometry and silhouette, but have these elements functionally attached. So another layer of development was working with the robotic experts. We came up with the idea, we'll discuss more in detail, but of using a robots, printing robots as the builder for this ice shell. So the idea was these blue outlines would be where the robots would basically climb up and down and sideways to print, to reach all the areas necessary to build the ice shell. And then the idea was that these the necessary area would be actually a track created by the ice. So this is basically taking the outside shell of the ice and showing the track where the printing robot would basically run around and climb. So it's a spiral configuration, so they can go sideways or go up and down. So this is finally the final presentation what we submitted for the final submission. So this is the plan showing 4 levels we have: the connection, 2 airlocks connection at the bottom. One above would be the laboratory, and then library and gym, so communal space, and then above that would be the 2 bedrooms, and top would be the penthouse, sort of with a big window and a gathering space, and the kitchen, dining, big wardroom, and in between are the hydroponic garden. That's triple height, basically goes all the way up and connects all those spaces with the green. You can pass in between your daily routines, and the middle would be the lander with all the mechanical and the plumbing, vertical circulation, and so forth, the bathrooms. And finally, this void, the garden, or we call the front yard, where we have basically a buffer space that don't have particular program, so it's place you can wander out and think whatever you want. So it's somewhere you can have privacy, basically. So
and the venting too. That's the space that would basically take all the venting of the habitat, right? So we could vent into this intermediate space rather than into the kind of outer environment of Mars.
Yeah. So what we saw was, if everything was programmed, the requirement was this 1,000 square feet. It's packed with program. And we saw that if every inch of the space is programmed, then people go nuts. We need some space that don't have any need. So that's part of the reason as well. So this is in section. And also you can see the printing robot hanging there, fixing, doing what it needs to be done. So this is, that's at the bottom is the water tank and all those levels we just explained. This is a 3D printed model, not ice. This is resin, a 3D printed model we submitted. So the height is about 50 feet, and the short direction is 50. The long distance is 75 feet. And this is kind of imagining the arrival. So this will be built automatically by the robot. So the first time people arrive, it's there. And this is how the docking happens with the rover and the structure at the north side. And entering from the south entry to the inner shell. So this space, you don't need the pressurized suit, like a big spacesuit. You need the oxygen, but you can have almost like a high altitude mountain climbing gear kind of works. So this is from the lander going up, looking through the bedroom beyond to the landscape beyond you. And this is looking up from the bottom all the way up through the garden with the natural light coming. So finally, the top quadroom, we have the big view, the gathering and the plants around coming up from the garden. So some night view. This is the rover approaching to the docking. And view in a bigger landscape of Mars. So what happens is the ice not only provides natural light to the inside people, but at night actually glows because it's translucent. So we thought that was a kind of a nice gesture as kind of a light, like a crystal lantern of the human civilization in the dark Martian night.
Do you have a question? Yeah, just so you rejected the
plastic bubble sublimation technique for the ice, instead you're going to use a printing, like these robots for printing.
Yep.
But also, just a moment ago, you were saying, you know, like when you first arrived, the robot would have already, so you land a robot first, the robot prints out this thing. How do you get, your vehicle is the thing that you live in the space, no? Your landing module
The lander
is what you live in.
Well, the lander in the structure is that comes without the human.
There's a vertical if you go to this section. That vertical lander. So all of this gets either landed or printed before humans arrive.
That's not just because like in previous ones, like that's what would carry the humans to Earth, right?
Right. So in this example, that's what carries the robots to Mars,
and then
the humans
a
come like a year and a half later.
Okay.
We'll get into the detail of the topic.
Yeah, it's a multi. They're going to be sending stuff in multiple missions. They're going to be caching food. They're going to set up a power station.
Yeah, no, it was more just because in all the earlier models, the actual one with the space, like the humans would land in, that was being used as the core, and then like, how are you building around?
Yeah, no, that's definitely the precedence. The lander is what the crew.
Yeah, this whole competition was framed so they will come without the people, and then people arrive later after the structure is done.
So scientific background. As the previous chapter shows, we focused on layered space, and then scientifically it is for barrier for radiation and temperature, atmosphere, and pressure control. So this is early sketch of our layered space. So left to top, this is so form is more like ice cube, but the strategy was the final one. And then, so this has 2 layers of ice shell is printed inside of the inflatable material on the Ciardullo foundation. And then the lander and the most inner layer of the ice has mixed air of oxygen, nitrogen, carbon dioxide, and toxic oxygen. And then aerogel pellets are incorporated with inner layer, and the temperature is lower in outside layer. Temperature is lower as outside layer. And then the sketch, this side one is a more area one, and then also showing the layer space, and then form is more rounded. And then, solar radiation ice. Ice absorbs a short wavelength radiation harmful to the inhabitant, but allows visible light to penetrate and even reflect within the interior space. But when we say radiation, it is not only UV radiation, but also high energy particles such as galactic cosmic rays. It's called CCR, and the solar particle event, SPE, it's life cycle in solar storms, which also has to be blocked. The GCR, which are extremely energetic but very, very low cracks, and SPE or solar storms, which are not as energetic but much more intense. So how we calculate war sequence? On Earth, we are protected by an atmosphere about 1,000 grams per square centimeter sequence. Mars atmosphere, by contrast with Earth, it's only 20 grams square centimeter sequence. It's straight up, and then it varies with altitude on Mars. So for SPE, storm shelter of a typical spacecraft is 20 grams square centimeter. NASA would like to have storm shelter to have 40 grams square centimeter shielding. So we want to have habitat to at least be as good as storm shelter. So we want to have the total shielding to be on the order of 40 grams square centimeter inside our core habitat. So this will be comprised of Mars atmosphere outside of the air, and then outer structure, and then the air contained by inside, between inside and outside shelter, and the inner shelter. So all this prevent radiation, total. So here is simple calculation of the wall thickness. Since Mars provides maximum 20 grams square centimeter, our ice should provide another 20, which we can distribute between the inner and outer shells. And we can ignore the air, but in reality it does add up as an additional safety measure. So in this case, minimum 5 centimeter thick ice on the outer level can be a perfect habitat from storm. Ice column on the right side is calculation of ice thickness by our consultant. And it is also confirmed that total 20 centimeter thickness is probably adequate for shielding from TCR particles at the chosen location. So this is the window idea. Good news is that at the horizon, the thickness of the Mars atmosphere, so this direction, is more dense. So it's between 15 and 20 times greater than the value in the beneath direction. So this direction, 15, 20 times bigger than this direction, atmosphere. So because the windows are facing towards the horizon rather than in the zenith direction, we can design transparent window without or maybe minimum layer of ice in order to achieve clear view. So to those windows, WETFE membrane layers are applied, which contains helium as insulation. The added atmosphere thickness in that direction should more than compensate for the loss of protection due to the removal of the ice. And then another aspect of the this is about the pressure and the ETFE membrane. A transparent and free closed ETFE membrane reinforced with tensile deneema is deployed from lambda and inflated from pressurized boundary between the lambda and the margin exterior. So this membrane, precise manufactured on Earth, is critical protection for the future ice shelf, preventing any printed ice from sublimating into the atmosphere. We ensure water will remain in its solid state. So by creating an interior atmosphere at 70 kilopascal, similar to the space shuttle, keeping the temperature at the surrounding Mars surface temperature, which at this latitude will remain below freezing all year round. So this is a sample of ETFE membrane with deneema strands. And then this is the structural analysis of ETFE membrane, because the air pressure from inside is this ETFE membrane that pressure. And then this is the silica fibers that reinforce ice. And then this is about temperature. So the deneema reinforced membrane is the only pressure boundary. Temperature. Translucent hydrophobic aerogel layer with U values of 1 watt square meter Kelvin and light transmittance of 66% is printed between the inner ice shell and the inhabited programmatic spaces to ensure thermal comfort. A porous substance, 99.8% empty space by volume. This additional lightweight material brought on lambda from Earth serves an efficient air gap to create the necessary thermal break. The insulating layer enables the inner volume to achieve habitable temperatures without melting the ice structure beyond. So this is a sample of hydrophobic aerogel. And then finally, that is air competition and the ice relationship. So summary separated from the habitat interior, the occupiable frontier that is inside of the outer the first layer. The frontier pocket just inside the outer shell previously provides a truly unique protected neutral zone that is not entirely interior or exterior. It enables astronauts to experience the outside without ever doing an air with the APS. So this zone space demonstrates a new liberating and revolutionary definition of living extraterrestrially. That is celebrates the novelty and wonder of living on Mars. The ice offers a boundary that can mitigate exhaust from the habitat and manage the critical cyclical relationship between the exchange and transfer production of oxygen and CO2. So this is the final ice shell design.
So I'm going to talk about additive manufacturing. Thanks. So OSAP had mentioned at the kind of beginning of this that the competition was sponsored by both NASA and America Makes, and that collaboration is in part because of the growing trend of using 3D printing in construction. And this is a growing trend both on Earth and also kind of extending to planetary construction. So I'm sure a lot of you guys are really familiar with kind of what additive manufacturing is, but it's basically 3D printing, which is creating a 3D object by depositing layers of a material, and as it builds up, it creates a solid form. There are kind of a lot of studies that have been done, primarily over, I would say, the last 15 years in 3D printing, of what kind of materials you can use, the compounds, the machines that you use to 3D print an object. And one of the studies that has kind of developed and that's become really popular in manufacturing items on Earth is something called sintering. And that's basically the process of creating a compacted and solid mass by heating up a material until it gets to a point that it condenses and becomes less porous but doesn't actually liquefy. And so in the kind of architectural studies that we developed over the course of this project, sintering was one of the types of 3D printing that we used, and then the other is obviously 3D printing with ice. So 3D printing uses today are a lot more widespread than I think people actually realize they're used. I have kind of a list of some of the common uses for 3D printing, and 3D printing has a very high level of precision. Objects can be made pretty quickly. They're starting to take over, instead of doing things by like injection molding or casting, people are starting to 3D print objects. So of sintering, some kind of common examples of that, glacier formation is kind of a natural form, and that's basically the creation of ice by compacting it so much that it becomes an incredibly hard, dense mass. And the strength of a material is often enhanced through the process of sintering. Volcanoes, the creation of glass, all of that, the lava, that's all kind of examples of natural sintering. And then on the right side, I'm showing some manufactured examples of sintering. So they do this a lot with metals, particularly metals that have a really high melting point. And that melting point is too high for kind of traditional methods of manufacturing. And so they've switched to this concept of a furnace or of laser heating. And NASA had kind of taken notice of this process of sintering. And this is a study that they did looking at the feasibility of sintering on another planet, or on the moon in this case. So basically what they did is they took the dust equivalent on the moon and experimented with laser heating it to see whether or not they could create a structural foundation. And these were the results of it, and the studies were actually really successful, leading NASA to think that sintering is a kind of feasible method for the future in terms of building on the moon or building on other planets. So that kind of takes me to our project in particular. So you see on the left two of the robots that we developed, the two robots we developed for this project, and Jeff is going to talk about the robots in more detail. And then on the right, you see the kind of double skin of the ice structure that we've created. And I think Masa mentioned this, but you see the ribbing on the ice structure, and that was created as a way to basically create footholds or tracks for these robots. So because 3D printing operates by kind of laying down deposits of material, often in a kind of spiral formation. So we took advantage of that and kind of played up the spiral nature of it to create these ribs that the robots could latch onto and climb vertically. And I think something important to note about our project in general is that we didn't assume the invention of anything 20 years in the future. We kind of took existing technology, we took existing materials, and we figured out a way to reinterpret them or to recombine them in progressive and innovative ways. So, for example, we were working with kind of a robotics expert who's been incredibly helpful throughout this process, and he has done some studies with vertical climbing robots, and that's a robot that a lot of companies are starting to use for construction. And then the other component of the robot, which is critical to 3D printing, is the nozzle. And that's basically the place where the material comes out, and what makes the nozzle critical to any 3D printing process is that it's the control of the amount of material, the pressure, the temperature at which the material comes out, and that's really how you control what object is created. So all of this meant that we needed, since there obviously aren't tons of structures printed out of ice on Earth, it meant that we wanted to start looking at the feasibility of it before we submitted this project. I think it's also important to note that OSAP had mentioned that this project started before they had kind of discovered liquid water on Mars, but one of NASA's kind of foundational concepts in terms of exploration has been a follow the water approach. So water has always been incredibly important to NASA's exploration. So when we took this project on, we kind of adopted that same credo. And so we really wanted, in addition to using indigenous materials, we really wanted to use materials that NASA considered the kind of the building blocks of life and life on other planets. So experimenting with how to 3D print on Mars meant, obviously, the conditions on Mars are incredibly different than the conditions on Earth, so we had to kind of approximate what that environment would be. And as Yuko and Masa described, we are taking advantage of the incredibly low pressure and incredibly low temperature on Mars in order to be able to 3D print out of ice. And dry ice on Earth has very similar characteristics. It's solid carbon dioxide that has a tendency on Earth to sublimate, which is the transition of a material from the solid state into the gaseous state. And that's exactly what happens to water ice on Mars. So we started with dry ice and started trying to figure out a way to print that because it felt like such a similar condition. And what we discovered is that dry ice always comes in kind of these like pellets or ground up kind of pieces, and they're incredibly hard to manipulate. So we moved from dry ice into liquid nitrogen. And the advantage to liquid nitrogen is that it's a liquid. So, and kind of as you saw with the nozzle, one of the important components of 3D printing is getting a material to come out of a nozzle and being able to control the stream. And so with liquid nitrogen, we were able to do that. And the concept with liquid nitrogen was because it's so cold, we could spray out of one nozzle liquid nitrogen and out of the other nozzle water. And the kind of theory that we were working under was that the water would freeze on contact with the liquid nitrogen. And so these are kind of incredibly DIY basic studies that we did. And you can see on the right kind of the small formation of a little ice sculpture. And that we were excited when we saw that because that in our kind of initial prototyping was proof of concept that you can build water and you can build an ice sculpture or an ice object or something using using the spray of water. So from there, since we only had 3 months that we were working on this and we're developing kind of the architecture in the background, we kind of transitioned over to looking at groups who have printed with ice before, even if they were using slightly different methods. And there's a group in Montreal who has done some ice printing. So we reached out to them and started working with them on our form. And the way in which they 3D print ice is they deal with a chamber that's cooled to -8 degrees, and they print a combination of water and something called methyl ester. And methyl ester, because it cools at a temperature lower than ice, what they can do is they can print 2 layers of ice and then a layer of methyl ester and then 2 layers of ice and a layer of methyl ester and keep going like that. And what you end up with is what you see on the right, kind of opaque form. And so you see on the left the ice, the addition of methyl ester, and then the kind of final form on the left, pre a kerosene bath. They soak the model in kerosene and melt and collect the methyl ester, and then what is left over is a transparent or translucent model out of ice. So you can see on the right, that's kind of one of our prototypes of our model. And these are a couple of other versions. We did a couple of 3D prints with them at various scales. We wanted to test both the light qualities of that, since that was so formative for our architectural design, and we also wanted to start looking at the structural components of it. Pretty critical to our design was that we were not bringing material from Earth, since that's been a huge barrier to printing large habitats or settlements or anything on other planets. And since we're proposing really just using ice, we needed to make sure that it was self-supporting, that we didn't have to add any kind of scaffolding or other material to it. And so you can see Masa had showed the kind of STL, the plastic 3D printed model that we had done. So that's on the right, and then on the left, it's a little hard to see on the bottom, but on the left are 2 views of the ice model. And what's pretty incredible is that the under light and when the 2 were next to each other, they are incredibly similar. So I think we were really excited to see that a lot of the kind of theories that we had developed over the course of developing the architecture for it held true when we printed the ice. Sure.
Sorry. In the end, what's the thickness of the exterior wall?
So what we discovered, and that's not true for the model because everything's scaled down, but you can print it at 5 centimeters thick, and you still have for the exterior.
But structurally, that's enough.
And structurally, that was also enough. Yeah, that was something that we worked.
And that provides enough of the radiation protection as
well?
It's
definitely enough for the radiation protection. And looking at them for the
5 inches.
5 inches.
5 inches.
5 centimeters is enough for radiation.
So like 12 centimeters or something like that.
I know that's enough for radiation, but I don't know.
The structure,
the design is much thicker.
Structure it tapers to the top, so the bottom is thicker, and for the top you don't.
Right, it's got a natural arch quality.
Exactly. But for radiation, it can be protection. It can be really thin. That's one of the advantages to using ice, is that it's one of the most efficient.
It has surprisingly good radiation protection.
Sorry, it's the biggest ice model you made.
The biggest one that we made was 12 inches, and that's just because it's limited by the machine, the robot basically that they had in Montreal right now. And for it to print the 12-inch model, it took about 2 days.
Sorry, just other technical stuff. But total volume of water needed to make the structure?
That is a good question that I don't know if I can answer. I don't think we can. Yeah.
How did you guys do that? By
So
like
the reason
liters of water.
The reason we don't know it on the top of our heads is because the one luxury we do have in this project is time. We could essentially source the water from X depth and Y.
That was going to be my next question: is how big is your water mine?
Right. So the answer is it would just be as big as we would have to find out when we landed. So you would use the best remote sensing information you have, and you would land in a latitude that was
is watery.
Yeah, that had water. Right now, we're proposing landing on a site that has a water table no deeper than 20 centimeters. So we would essentially need to get down there. And there's 2 kinds of water. One is solid, and it's just like that's the ice table. But the other one is water vapor crystals that are kind of embedded in the regolith itself. So you could sort of bake those out. Yeah.
I mean, it's the process of sublimation basically purify the water, so you wouldn't have the regolithic component to it anymore, which helps with the
with nitrogen. Careful the protector.
It's tough to. So one of the things that you're probably noticing while you're
here's ice.
That is one of the things that we discovered, and this is apparently.
Pass this around. Just don't touch it.
This goes,
exactly.
This goes back to the kind of comment that the nozzle is critical. And this is kind of perfect evidence of it. One of the things that we discovered is that the stream of water, if you're going to print it this way, the stream of water compared to the stream of the liquid nitrogen has to be exactly right, and there can't be that fast of a stream of water because the water will otherwise melt the ice that you've already printed. And so it's a kind of perfect balance of letting out just enough water that it's
just like this slow.
Yeah, exactly. Because what you don't want is you don't want it either melting the ice that already exists, or what we discovered when we were doing the test is if you don't have the correct kind of pressure or stream, the water will run off before it has a chance to freeze. So I mean, in all of that, those kind of DIY tests are definitely to approximate what would happen on Mars in some ways.
Though you would not actually need to be.
You would not need the liquid nitrogen because it's that cold. Exactly. Okay. So on Mars, all you would need to do is you would need to control the pressure, and you already have really low temperatures. Right. So by creating that,
it'll probably actually be easier and a little more like.
Yeah, and actually, Mars has infamously little nitrogen, so we could never use this even if we wanted to. It was more just like
a way to approximate.
Yeah, exactly. Like what can we actually do in like 2 weeks or whatever?
Right, because obviously you can't freeze the nozzle when you're doing it's a reverse process for usual sintering here.
Right, exactly. And so and Jeff will talk about the sintering component of it a bit because we're using sintering to basically create a foundation that grounds the lander, and then everything else that we're doing from there is the 3D printing of the ice. But in a lot of ways, 3D printing on Mars would be significantly easier because you're only worrying at that point about controlling the pressure and to some extent controlling the temperature of the nozzle. That was one of the things that when they did this ice print in Montreal, they're printing at -8 degrees, but the nozzle itself is at 68 degrees because they have to basically have just enough time for the water to come out as a liquid stream before it freezes.
It stays for a moment. And then
and that part of the process is very similar to what we would do on Mars because the chamber itself, the environment is so cold that all you would be doing is you would have like a heated nozzle basically to let it come out.
Oh, Justin, you had a question. Do you want?
It was asked and answered.
Okay. So our decision to use water had to be really supported and secured by a guarantee that our process would not contaminate water itself, because water is the essential element for life, and it's something that we're proposing to use for a structure because it satisfies all these other pragmatic. It provides all these benefits to us, which amazingly they just keep on coming. But if we were just to start grabbing water from the environment without a way to separate it out from the toxic environment that it is, we would essentially shoot ourselves in the foot, and it would all be pointless. So we could have had as many as 4 robots if we really wanted to. We could have had a robot to print the foundation. We could have had a robot to get the water. We could have had a robot to print the outer shell of our structure. We could have had a robot or a robot arm to print the inner shell of our structure. But we ended up getting them down to 2. And that is largely in sync with this harsh dichotomy of Mars, where you have, on the outside, you have this incredibly harsh hostile landscape, which is not only toxic but abrasive, physically abrasive, full of dust, which you don't want to touch, you don't want to respirate, you don't want it to get anywhere near your machinery. But on the other hand, we're using water, so we really want to separate the uses of these things. So we have 2 robots, and you can see here how they're stowed away in this garage space of our lander. We could fit up to 9 of the upper EBOs and 4 of the lower. Our EBO is our ice printing bot. It consists of a printing arm with a triple nozzle. The triple nozzle contains a nozzle for ice or water, a nozzle for fiber reinforcement, and 1 for aerogel. And Yuko explained how aerogel is coated on the inside of the inner shell to protect the ice from the waste heat of our lander. And the wheels are on a sort of double axle, the typical axle that all wheels have, but then one that's perpendicular to it that allows the wheels to grab ice in order to climb the ice. So it's a system that prints its own track and corkscrews its way up to the top. And this was chosen in a very heated, prolonged debate over a robot arm. That was the hardest debate, I think, because the robot arm would essentially print itself in. It would basically print itself shut. So you would either need a robot arm and little bots, or just the little bots. So we decided to go with the little bots and keep them as light as possible. And because they're so small and light, we basically need a tether. So we have these things tethered, and they start wrapping around and capping off the structure. And here's what it might look like as we're closing off the hostile exterior in our glowing interior. The other robot is our Wasibo. It's a sort of like a linear factory, if you will. It's composed of a water holding tank, an ice block laser cutter and claw arm, power, various other subsystems, a bake chamber, a shovel, and a grinder. So once it's out and about, it collects regolith in a shovel, deposits it atop its processing chamber, receives it through a slot, and then proceeds to bake it, process it either with a combination or both heat and pressure. And this would separate water out, as well as other volatiles which are essential for life support and plant growth. And then it would collect them in a tank, which is, essentially it's a distillation process. And the port at the back would plug into a hose, which I'll show you now. Once it's collected that regolith and separated out what it needs, it can actually let loose the wasted regolith that's now dried and lacking in materials into a thin layer. And essentially with this sort of like CNC style router, it could sinter it as a printer would as it's driving forward, and leave behind a band of firm regolith that it could print in a spiral fashion or some other print path. And the other mode for the same robot, which is the cool thing about collecting water and printing regolith, sintering regolith, is that you essentially need the same processes. You need a way to collect regolith, and you need a way to heat it. So you need a system that provides power for pressure and heat. So we use essentially the same mechanism to cut out blocks and put them in this chamber, where we then undergo the same process again of distillation, essentially. And so this is what it looks like before. This might answer a lot of questions about how this thing gets built. So once we land, our lander is essentially a cylinder, which almost all, keeping track in the slightest, all space architectures ends up being, or has so far been, cylindrical due to the rocket geometry restrictions. So we would essentially land this seed and from there we would drop our wasibos, and they would begin to scout and collect, right? But one of the things they do first is to pull out the hose to the edge of what would be the future foundation, and also drop a reservoir bag, which would get filled with water and printed around at the same time. So you'd be filling a vessel and then creating the vessel. And that hose is forever available to the robots, even for after the humans arrive. So the printing occurs, the sintering occurs. You built a controlled surface for your one chance delicate habitat, and you begin to inflate your membrane. And after you've inflated your airlocks, you begin the process of ice printing. Now, notice that the ice robots went from the sort of garage space to the interior that was after it was inflated, while the exterior robots, the Wasibo, were basically outside the whole time, and they're always out there. So you never have cross-contamination. And this continues until you complete the outer shell, and then you complete the inner shell. The plants can be initiated, the growth can be initiated from these hanging vertical gardens. The habitat would enter some sort of standby mode, and it would indicate to the astronauts who are either en route or waiting for this green light to come, and essentially would await the arrival of the crew. And the Wasibo essentially can park themselves as a single centipede that would feed the one hose they have. And then the crew is able to carry out their mission, and they arrive in this ready to go. So that's it. Any questions?
I have a question. It seems that ice is actually the idea that no the change presented, there is more that you guys work around to find all these solutions. And I was wondering how, within the process, if the ice idea came in at the beginning and you just work on developing around it, or if you try many other possibilities. How was the process of coming to that idea and developing it further?
I think we came across ice in parallel to working across all the other difficulties of this like tyrannical problem of the rocket and how much we can land on Mars because of these very oppressive mass ratios. You basically have to. You can't just say I want an ice house, or you can't just say I want an underground bunker. Like, you have to start with what you can start with and get into on the surface safely. And after we were researching Mars as a landscape, and these things just kind of emerged. I don't know if there was pretty organic.
I think also, a lot of our conversations at the very beginning, we all come from an architecture background, and so all of us are trained to think about space from the perspective of the human, and that came up very early in the conversation. So we definitely did look at sintering regolith. That was kind of what we saw in all of the precedents. That's what a lot of the other competition entries looked at, and that's in part because that has been studied quite a bit, whereas 3D printing ice has not. But it felt like we were missing an opportunity if we kind of kept along that path, because history has shown us that light is incredibly important to humans, and there are very, very few, if any, examples of building on other planets that have really taken light into consideration, and that's partially because the environment is so harsh. And so when we discovered that there's an abundance of kind of ice on Mars, that material kind of opened us up to the idea of, okay, that's a translucent material. How can we start to incorporate that into the habitat? What would it mean if that was kind of the primary building block? And then I think everything kind of was a domino effect from there, that slowly the regolith kind of fell by the wayside, and we realized that ice could achieve kind of all of the problems that we had run into up until that point.
Yeah, it actually came right before the first deadline. Like I explained, there were 3 deadlines. It was very intense within the 4 months. And the first deadline, like maybe a few days before, right? I mean, we got to talk about ice. Almost people couldn't take it too seriously in the beginning because it like sublimates, right? So how can 3D print ice that evaporates like dry ice on Earth, right? So then I think a few days before the first deadline, we were kind of having a bunch of ideas, mainly regolith, and trying to narrow down to a proposal, right? But I think then we found out into that the ETFE pressurized volume. Then within that we can print ice, and unfortunately that idea, like you mentioned, didn't work because after we worked with real engineers, they mentioned it's possible, but then it wouldn't be as strong or solid or transparent as we want. It'll be more like ice cave, you know. So eventually we went to more, the novel controlled printing method that happened in the middle between the first submission and second submission. But that was part of the development. But I think the idea really, everybody kind of gravitated when we figured, there's the idea, this concept, technical concept of having a ETFE transparent volume, and within that we can actually control it.
There's a question in the back.
Hi. So I have a question about the transparency. You're talking a lot about light, but isn't Mars? You guys talking about how dusty Mars is. I don't think that it can be like transparent forever. So it'd be pretty dusty. Is there any way that you guys are cleaning it? How slick is the surface? Are the robots cleaning the outside? Is it like how is that surface?
We don't have window cleaning
robots.
However, it's a problem that, in a way, you solve by not providing any windows. You know what I mean? So if you open the habitat to the landscape and you give humans access to circadian rhythms, which we're lucky the day's only 40 minutes longer, then you are essentially providing the opportunity for this to even occur. Another thing is that the habitat, at least for the brief, this is not a colonization mission, but an exploration mission. So it would not extend more than a year of their stay in the habitat. And the third thing I could think of is that actually the Phoenix lander, I believe, had solar power. The current Curiosity has nuclear power, but the Phoenix, and that's why it's lasted so long, had solar power, but it was diminishing through time because of dust accumulation. And this great thing happened where a dust devil passed right over it and cleaned it, and you could see the power spike up again. So there is weather on Mars, so it's possible that would help as well.
I mean, one of the considerations we did think about that, and the verticality of the form. The form is actually quite vertical, so the dust would have a difficult time accumulating on a vertical surface. And the outside of it is actually ETFE, which is quite slippery. And we talked to the manufacturers, and the ETFE is pretty abrasion resistant, so it wouldn't even start to get etched by the dust. Like that was another concern, that you would get the kind of the dust blown kind of sandblasting of the surface. But actually the regolith on Mars is so fine and so light, it's almost like a down in a way. So like for example, the Martian movie is hugely inaccurate in their portrayal of the dust storm. The wind doesn't have as much force as it does on this planet because the atmosphere is so thin. So even though it's windy and it's kicking up this really fine dust, it doesn't really have that much kind of abrasive power or let's say force to it. So for those reasons, we felt like we didn't need like a cleaning regimen or like like some way to actually go out there and kind of scrub the surface. Back there again, in the back, sorry.
Me?
Yeah.
I think you started to answer this by just saying that it's limited to an exploration mission and not a colonization. But because of the language that you're also using in terms of the sort of psychology and this like wonderful base idea of light and a window, as simple as it seems. I'm kind of curious if this is, and maybe this also touched the contamination issue, if this is a completely hermetic closed system, or it's something that through the EBO and the if there's a possibility of then starting to sort of populate one, like another one, or some kind of interaction with a larger structure, like can it grow beyond its initial form? That's so one. I have several questions.
The scalability of it, whether you can have like a village.
Yeah, or if it can be like if there could be an annex, like or if there's like some reason halfway through the year you're like, oh my god, we have to extend this project because of something that we discovered. We have to make this new chamber. Even it's either that or like, oh, we have to send like 4 other people there. Can we build another one without sending another preface? All these people.
I think unfortunately it depends on each lander is a habitat, right? So because the UTFE is sort of wrapped around the lander when it comes down and it's inflated from the lander and the systems all come out of the lander, it's basically each lander is a habitat. So if you wanted to extend the system, you would basically send another lander.
That being said, though, it also doesn't mean that like the next lander could be a lander carrying humans, right? So it doesn't necessarily mean that every lander would have to land first, and then you would wait a year and a half and then send another lander. Like this, the kind of premise of the competition and in general about 3D printing on other planets is that since it's kind of a new concept, that you would want to get the habitat up and running before you send humans to it. But if you had this up and running, then in theory, the next lander could be the lander that's carrying humans, and they could build their own habitat and potentially like live in this habitat while they're waiting for it to build. It's at its very base, it's a pretty simple concept. Like you need a balloon, a pressurized balloon, basically, and these 2 robots, and you can print what you need.
Just a quick side note about that, like in terms of humans following the deployment of these things. One criteria NASA has established is that they need to make sure, like the green light for sending people, is that they've already manufactured enough propellant in situ to allow for the return trip. So for the return trip, right? So until they actually manufacture the propellant, they're not going to send people, right? So that's like one of the criteria. So there's like multiple landers, multiple systems that are sort of landing and establishing like this base, right? And kind of,
And my second question is sort of in terms of not contamination in terms of like a vapor or whatever, but so much as like, and I wouldn't call it contamination, but since you prefaced the whole presentation with this architectural idea of like leaving an iconic or having an iconic form, I'm sort of curious of how you all together have been thinking about it as a trace also. I mean, if it's a 1-year mission, that like then there's this, is it something that then the EBO, fills in entirely? And because I would imagine like also because it's on the inside, it's slowly getting very minimally maybe like smaller and smaller space as it's being fixed. So I'm sort of curious of like what happens, what's the extent of that? Does it, lock itself up completely and become this sort of archaeological?
If they leave it, maybe they print it solid and it becomes a reservoir or something. Right. That's a great.
What did the
I like the way you
found with a flag and glass.
No, I mean I think the idea of the icon and of the trace that came up a lot in our conversations because we wanted to obviously, since if you're putting humans on a new planet, you want there to be something iconic about that. You want there to be kind of this recognizable beacon, both from the sense of coming from Earth and having an icon to kind of go towards on Mars, but also once you're on Mars. But there's a kind of balance between that and not wanting to, go in and completely destroy the surface of another planet, right? So I think it helps that we're dealing with indigenous materials. I think of everything that we're putting on here, really the lander is the only foreign element. So, I mean, I think there are a lot of ways you could think about what would happen if humans were to leave and never come back. You could break the ETFE membrane and everything would sublimate and you wouldn't have that, you would just have the lander left, or you could do what you're talking about and kind of leave this trace of human settlement here. I think I think that's like a fascinating question and a probably totally other study of what we would want to do with it.
Are there, besides losing the view, are there any disadvantages to building inside a crater?
Well, so the two things that would prevent you from sighting yourself in a crater, you're saying for protection, right?
You can get more area probably if you.
You mean well, so I think the craters on Mars are not at that scale. So you would be sighting in a crater that you may not even see. You actually might see the horizon before you see the rim of the crater. Okay. Keep in mind also Mars is much smaller than Earth, so the horizon is closer and the atmosphere is thinner, so everything looks closer anyway. I don't know. Most of you had something on your mind right now.
No, I think it's just purely mechanical. Like the landing ellipse is so large that you might target a crater, but you might land somewhere outside of the crater. I don't think they have enough accuracy at the moment to be able to land inside of a crater. And then, when you talk to when you watch the presentations by the astronauts, and their concerns in terms of like driving rovers and the inclines and slopes that they have to navigate to actually get out and do science. The crater poses problems because like getting in and out. Like, are you going to start to do some landscaping to allow that kind of access? And so I think it was just purely the ease of use, the ease of like landing and kind of assuming a homogeneous, like flat-ish landscape. Yeah. In the back?
Just a technical question. Do you guys happen to know whether ice forms on Mars at the same density as it does on Earth?
That is a really good question. So we do know the makeup of ice. I don't know that the density has been tested. I'd have to look at that honestly, just to tell you. But it's. I guess the short answer of that is that it should be the same density because it's the exact same makeup. That was something.
The inner cabin.
Exactly. I mean, the kind of the concept of creating that pressurized bubble is that you create an environment that you can control with very little effort, basically. Like you're not trying to control the temperature. There aren't a lot of factors you have to control. Pressure is the only one. But
it could even be a benefit. If you have less dense ice, it means you need less water to make it.
True, that's true. I mean, we did study the kind of structural components of it, so that we looked at the gravity component of it, which would potentially factor into the makeup of ice, and we looked at what the actual components of ice were, but I don't know for a fact what the density is.
I think actually our goal would be to get it as dense as possible in terms of the clarity, right? Because the less dense it is, the more kind of air bubbles and the less transparency there is. So I think we'd want to try to get it as dense as possible. So like the pressurization of the interior is key.
Yeah, the only instance where the ice on Mars would be different is at extreme depths because of its own mass. But since we're not building nearly that much, it's just a matter of how we create a little bubble, create an ideal environment for ourselves, and then print.
Following that.
Shoot first.
Yeah, but I've asked all of this. I was curious about the power source.
That was kind of outside of our scope. We just assumed that there would be power there.
It was part of the competition that, and OSAP kind of mentioned this, that there's like there are a whole bunch of other things that are coming to Mars simultaneously, and they had kind of mentioned that peripherally in the brief, yeah, but they had asked us to focus just on the architecture.
So change of state is a bit of a energy stuff.
You mean for the water?
Yeah.
So that is actually natural. Oh, wait, well, yeah. So the phase change from the solid to the gas, that can be a naturally occurring.
No. But like when you're mining the regolith for the water to extract the water out of it, and then so now you have a bunch of liquid water, I assume, or you're gonna let it'll be liquid for a moment, and then you'll like condense it into like ice blocks, basically, so it's as dense as possible, right? Or actually not as dense as possible, it's denser, but
the sort of exact power or even rough power consumption of these things wasn't addressed. What we do know is that the construction of an ice habitat is lower energy than a construction of a regolith habitat, because the phase change is lower energy. So
then a century.
Sure. Yeah. So you have to get things through a nozzle, as Kelsey was saying, or change their state somehow. And regolith would need a lot higher energy to sort of mold and manipulate than water. And in both cases, you need excavation power. You need to be able to move earth to get to the water, or to get to the earth and use that. So that was out of our scope, though. So it was an architectural competition, as opposed to a mission architecture.
The other thing to note, though, on the phase change is, and one of the reasons why it's so much more energy efficient than dealing with the regolith, is that we were using kind of the Mars environment to our advantage, which is the particular temperature and pressure conditions on Mars mean that the only way for Mars to remain as a solid form is when the pressure is higher than the pressure that exists in the atmosphere. So that's why subsurface water is in the ice form, and it's because it's buried underneath all of the regolith, and so there's a different pressure condition underneath the regolith than there is in the Martian atmosphere. So and that's why in OSAP's kind of early slide where you showed over 4 days, as soon as it's uncovered, it sublimates. It turns into a gas. So in theory, if you had a robot that had kind of like a bag attached to it, and you basically uncovered the regolith and it would just sublimate into the ice bag. So you're not actually relying on power for that. And the reverse in theory would be true, is that if you then propel that gas into a pressurized environment, then it would turn back from the gaseous stage into the solid phase.
Are those environmental conditions constant? Like you had mean temperatures and low temperatures, but you haven't said anything about high temperatures?
It's why we cited it where we cited it. So we worked with someone who is really familiar with the kind of geology and temperature changes on Mars, and Alba Mons in particular had the right temperature range so that it would never get so hot that the ice would melt, but it was also basically that was kind of the primary concern is that it would never get so hot.
Yeah.
I think we're going to cut it off, and you guys can ask the questions individually if you don't mind. It's getting kind of late. Thank you all so much. I want to know what happens when those meteorites come.
Then the robots come back out.
All right. And if anyone, we're going to go up to for a little while, right?
Yeah, if
7 4. And if anyone wants to try, I think there's still some dry ice left in here. If you do it on this metal table,
if you're interested in visiting Genespace, we're one floor up.